the efficiency of traditional silicon steel transformers is as high as 99.5%, which is almost a perfect physical limit. But why do AI giants, at the forefront of technology like Google, Microsoft, and Meta, now prefer to sacrifice 2% to 3% of conversion efficiency and spend astronomical budgets to completely replace their data center transformers with solid-state transformers SST? Over the past few days, many viewers with deep backgrounds in electronics and electrical engineering have passionately commented below, questioning if lower efficiency means more waste heat, requiring stronger AC and leading to higher electricity bills. Are these tech giants making a loss-making deal? Actually, people have this doubt because conceptually, it's easy to confuse conversion efficiency and power factor, which are two completely different things. If we just take out a calculator and actually calculate how much power the power plant needs to generate, and then look at the terrifying effect of AI servers violently drawing power, which is like a meteorite smashing into water causing massive splashes, you will suddenly understand everything. You'll realize how accurately the AI giants have calculated this. In today's video, we are going to solve this biggest technical suspense, deeply dismantling the terrifying truth of sudden power surges in AI data centers and the truly irreplaceable value of SST solid-state transformers. I will divide this video into 3 main parts to provide the most hardcore decoding for everyone. In the first part, we will use actual electricity figures to calculate, debunking the myth that traditional transformers are really more power-saving. This is the biggest myth of the century, and I'll help you thoroughly understand the essential difference between efficiency and power factor. In the second part, I will use the physical phenomena of wave pools and splashes to visually explain to you how terrifying AI servers really are, and explain in detail what load stepping and harmonic pollution are. Finally, in the third part, we will break down the God-level black technology architecture inside the SST. Let's see how it transforms into the ultimate firewall that perfectly isolates the grid, trading efficiency for the absolute stability of the power grid. Now, let's directly enter the first part using numbers to calculate, breaking the myth that people confuse the most. What exactly is the difference between conversion efficiency and power factor? First, we must acknowledge the disadvantages of SST. SST uses a large amount of high-end semiconductors like silicon carbide internally. When these switching components perform high-frequency switching tens of thousands of times per second, they inevitably produce switching losses and conduction losses. SST will lose about 3% of electrical energy, which completely turns into waste heat. This is what we call lower conversion efficiency. In contrast, traditional silicon steel transformers, because of their excellent magnetic permeability and the lack of semiconductor high-frequency switching, their conversion efficiency can easily reach 99.5%. If we only look at this metric, traditional transformers definitely win. However, for grid operators like Taipower and large data centers, their biggest headache is not the few percent of conversion waste heat at all, but the power factor, which we'll abbreviate as PF. To understand power factor, we can use a glass of draft beer as the classic analogy. When you buy a glass of beer, there is actual liquid beer in the glass, and a layer of white beer foam on top. This liquid beer is the true real power, consumed by the equipment to do work, measured in kilowatts Q. And that layer of foam, which you can't drink but takes up space in the glass, is reactive power, measured in kilovolts kVAR. The total capacity of the glass occupied by both liquid and foam is called apparent power, measured in kilovolt amperes kVA. The power factor is the ratio of the liquid to the total capacity in actual industrial environments or data centers. As long as your load contains inductive components or non-linear switching power supplies, like those used in servers, the AC current waveform will have a time difference from the voltage waveform, meaning they are out of sync. This asynchronous nature creates a lot of reactive power foam. Let's pull out a calculator and show you the math. Suppose today there is a whole row of AI racks that actually need to consume 1,000 kilowatts of real power. If the front end of our data center uses traditional transformers, their efficiency is extremely high, let's just say 100%. If the racks need 1,000 kilowatts, they request 1,000 kilowatts from Taipower. However, because the high-frequency power supplies inside the servers generate reactive power, assuming the power factor is only 0.8, then 1,000 divided by 0.8 equals 1,250. What does this mean? This means Taipower's power plants actually must prepare as much as 1,250 kVA of power generation capacity and transmission lines just to feed this row of racks. This extra 250 kVA is useless foam. Even though it doesn't do work, it circulates back and forth inside Taipower's ultra-high voltage cables. According to physics formulas, current flowing through a conductor generates heat. This implies that this reactive power causes Taipower's grid lines to heat up severely, producing massive line losses and wasting precious grid capacity for nothing. So what if we replace the front end with an SSD solid-state transformer? SSD's conversion efficiency is only 97%. The racks need 1000 kilowatts, and because the SSD itself generates heat, it must request a bit more power from Typower, roughly 1030 kilowatts. On the surface, SSD seems more power hungry, right? But here comes the most amazing part. The front end of the SSD comes with extremely powerful active power factor correction. Through its internal chip algorithms, it can forcibly align the voltage and current waveforms to perfect synchronization, bringing the power factor close to a perfect 1.0. Therefore, 1030 kilowatts divided by a power factor of 1.0 equals 1030. This means Typower's power plants only need to prepare a capacity of 1030 kVA. Do you see this shocking difference? Even though traditional transformers themselves don't generate much heat, they force the power plants to prepare over 200 kVA of reactive power to run idly back and forth through tens of kilometers of power lines. These line loss wastes along the way have long far exceeded the tiny bit of power saved by the transformer itself. While the SST generates a little heat itself, it drastically reduces the total capacity demanded from the grid. When this scale is magnified to consuming hundreds of megawatts, meaning hundreds of MW in super AI data centers, if the power factor is too low, not only can Typower not provide such thick cables for you to use, they will even issue astronomical power factor fines to the data center. This is why major companies would rather sacrifice a little bit of their own conversion efficiency and absolutely ensure the power factor is perfected in one go. Next, we come to the second part, to discuss the highly terrifying vampire-like characteristics of AI servers and the devastating pollution they cause to the power grid. In the field of industrial automation, we are very familiar with CNC milling machines or large servo motors operations. When the machine is on standby, power usage is very stable. But once a machining command is issued, the spindle motor must, within fractions of a second, instantly accelerate to tens of thousands of RPMs. At this moment, it generates an extremely huge starting current surge. Today's AI computing centers are simply the ultimate, insanely magnified version of this industrial phenomenon. When tens of thousands of NVIDIA flagship GPUs are waiting for data in the server room, their power consumption is actually at a relatively stable low level. But as soon as a large language model training task with hundreds of billions of parameters, or massive amounts of inference weights, is instantly dispatched via fiber optics to the GPU cluster, these tens of thousands of graphics cards will, in just a few milliseconds, a thousandth of a second, instantly spike from extremely low load to 100% full load computation. In electrical engineering, we call this phenomenon of current rapidly climbing in an extremely short time extreme load stepping. To make it easier for everyone to understand, we can imagine Typower's power plants and power grid as a broad river, and the power plant as a massive wave maker. This wave maker, precisely at a frequency of 60 Hz, meaning 60 times per second, sends out extremely smooth and regular AC water waves. Our ordinary household appliances, like ACs, refrigerators, and TVs, are like small boats gently floating on this water surface, riding the waves without breaking the regularity of these water waves at all. But the sudden power surge of an AI data center is completely different. When these tens of thousands of GPUs instantly receive a task and violently draw millions of watts of power within milliseconds, this is not a small boat at all. This is like an extremely massive and gigantic super meteorite, suddenly smashing at supersonic speed into this originally peaceful river. What happens when this meteorite smashes into the water? First, it instantly drains all the surrounding water levels. In a power grid, this is called voltage sag or voltage drop. Because the instantaneous current needed is so large, the voltage is rapidly pulled down. Then, an even more terrifying thing happens. A meteorite smashing into the water definitely doesn't just leave one hole. It stirs up countless chaotic and violent, irregular ripples and splashes, frantically spreading in all directions. These messy, extremely high-frequency small splashes, in electrical engineering, we refer to as harmonic pollution. If the front end of your AI data center uses a traditional silicon steel transformer, that is absolutely a disaster, because a traditional transformer, structurally, is like an extremely thick, hollow, super large concrete pipe with absolutely no blocking capability. Although it can send power in with extreme efficiency, it also freely allows the data center's violent ripples and harmonic splashes to flow directly backward into Typower's main river. What are the consequences of this? These high-frequency noises will travel along the high-voltage grid and rush into other factories or residences under the same substation. It will interfere with the operation of precision medical equipment, cause motors in other factories to overheat and vibrate abnormally, and even, when harmonics reach a certain severity, trigger misjudgments in the protection circuits of type-hour substations, directly causing massive protection trips, resulting in unannounced massive blackouts. Traditional transformers cannot solve this problem at all, forcing traditional factories and data centers to spend massive amounts of additional funds next to their distribution panels to install entire rows of huge, bulky, and highly aging fire-prone PEF-AC capacitor compensation panels, attempting to offset these chaotic splashes. Finally, this brings us to part 3. How exactly does the SST solid-state transformer arrive to execute this god-level rescue? Faced with the unethical meteorite-level impact of AI servers, instead of wiping up the mess afterwards, it's better to build an impenetrable fortress right at the source. SST is this ultimate firewall. The reason SST can perfectly solve this problem lies at its core: its internal active front-end and DC link technologies. When the SST receives type-hour's AC water waves, it doesn't send them directly to the servers, but first passes them through high-end semiconductor switches at the front end, converting the alternating current to direct current. During this AC to DC conversion process, there is a very massive capacitor module inside the SST. This is what we call the DC link. You can imagine this DC link as a super gigantic buffer pool hidden inside the transformer. When the rear-end GPU, this massive meteorite, smashes down, instantly violently drawing a massive amount of water, what happens? It is this internal buffer pool within the SST that instantly releases its stored water to withstand this impact, rather than directly reaching out and dragging down type-hour's main river. Because of this layer of buffering, the external power grid can barely feel how severe the load stepping was inside the AI data center. It perfectly resolves the crisis of voltage sag. Even more amazing is that the SST is an actively controlled device. No matter how disgusting the current noise generated by the high-frequency power supplies inside the data center, or how chaotic the harmonic splashes stirred up are, as soon as this pollution touches the SST's internal DC link, it will be 100% completely absorbed and physically isolated. The microprocessors inside the SST will continually monitor the status of the external grid at a frequency of tens of thousands of times per second, and control the semiconductor switches to ensure that the input end of the SST facing type-hour always only presents the smoothest and most perfect 60 Hz sine wave. It not only does not create splashes itself, it even helps filter clean the original noise within the power grid. What does this signify? This signifies that as long as you have SST, AI data centers will never again need to spend extra millions to build those massively spacious, high-maintenance power factor compensation cabinets and harmonic filters in modern data centers where every inch of space is precious. Saving this equipment space means you can squeeze in several more computing racks. Behind this represents revenue growth of millions of dollars every second. In summary, replacing traditional transformers with SST solid-state transformers on the surface appears to lose 3% of conversion efficiency and create a bit more heat, but within the overall macro engineering and business logic, this 3% loss is the cheapest insurance premium paid by tech giants to ensure the power grid does not collapse. With a minuscule cost, it trades for a near-perfect power factor, trades for the buffering capacity to resist sudden surges, trades for pure, unpolluted grid isolation, and paves the last mile for the future. 400-volt high-voltage DC power supply architecture. This is the most exquisite art of trade-offs in the engineering world, and it's also the true domineering reason why the SST solid-state transformer can completely eliminate traditional behemoths to become the next generation true energy heart of AI computing centers.